Hello everybody. In the last class, we had seen how to convert a truth table to a Boolean expression, for which we had seen min term based SOP, sum of product representation and max term based product of sum representation. And we had also seen how to realize it using AND bank and a final OR gate for SOP realization and a OR bank and a final stage second level OR gate for POS representation. And also we had seen NAND and NOR equivalent circuit for them. Now, if we want to have a more simplified or minimized realization of a truth table, do you need to go for algebraic simplification of the min term based or max term based expression that we have got, or can we have a better method? So, Karnaugh Map gives us a very convenient method to simplify a SOP or a POS based to get a SOP or POS based expression. So, we shall discuss this thing in this particular lecture, how to simplify. First we shall look at the how to represent a truth table in the form of a Karnaugh map, and then we shall also look at use of don't care in Karnaugh map simplification, taking up one example, and then we shall look at dual circuit and self dual function. So, in the Karnaugh map based representation, what we do actually, the truth table we present in a different manner. The truth table we had earlier, what you have seen that there are if it is a two variable truth table, this is y. So, 0 0 0 1 1 0 1 1, 4 possibilities are there and corresponding function output that you see over here. Okay. So, in the Karnaugh map based representation for a two variable case, we are having a rectangular space like this, where this side is variable A and this side is variable B. The values represent 0 and 1 for B. This column represents always B remaining 0 and this column represents B always remaining 1. And this row represents A remaining 1, this row represents A remaining 0. So, at the cross point you have got a combination of specific combination of A and B. So, this particular place is a combination of 0 0, this is 0 1, this is 1 0 and this is 1 1. So, all the four things that you see in the truth table are represented in the Karnaugh map in their respective location. Okay. And in terms of min term, if we look at it in terms of min term, then each of these spaces, if there is a presence of 1, so A bar B bar will be the corresponding min term, A bar B will be the min term over here, A B bar will be the min term over here and A B will be the corresponding min term. And also we also already know how to represent a min term in terms of its decimal suffix. So, this is your M 0, this is your M 1, this is your M 2 and this is your M 3. Clear? So, this is how we look at a two variable representation of a Karnaugh map, and this will be extended for 3 and 4 variable multivariable cases. And if we look at the truth table that we had seen before, or that is over here, before that the another truth table which is a simpler, only 2 1s are there. So, the corresponding output you can see that the function output 0 0, this is 0, 0 1, this is 0, output is 0, 1 0, this is 1 and 1 1, this is 1, right. So, this is what we can see as going as a mapping, and the one that we had seen before 0 0 it is 0 and rest of the 3 0 1 it is 1, 1 0 this is 1 and 1 1 this is 1. This we have already seen. So, this truth table when gets mapped to Karnaugh map, it would look something like this. Okay. Now, if you look at this representation and the kind of logical connection between input and output, what we can see that in this truth table, it is evident that the output is 1 when A is 1 and output is 0 when A is 0, irrespective of value of B, is not it? You can see that A is 0, output is 0, these two cases, and A is 1, output is 1. Okay. So, you can see the corresponding when a is 0, this was the 0, a is equal to 0 case, right. So, both are 0 and a is equal to 1, both are 1. Okay. And so, from the truth table we can see that the y follows a. So, we can write y is equal to a. So, which is nothing but where this row a remains at value 1 irrespective of the b changing from 0 to 1. So, b bar means here it is 0, b means it is 1 irrespective of b changing, for value a remaining 1 output is always y at 1. So, we can see and output is 0 for a remaining 0. So, we can write y is equal to a by grouping by looking at these two values which can be put together, grouped together. So, we look at this representation. So, again this 1 1 is present, right. So, this particular group can give us whatever if this 1 was not present, right, a minimized version of 8 which had been the case otherwise as a b bar plus a b, these two mean terms a b bar and a b, and we can it is well understood that from complementarity we can get a. Some problem. Okay. So, this is a, right. So, so this a comes over here, right, and if your this was not there, only b, this particular these two ones were present, that means this one and this one, right. Okay. So, this is the case when b is, these two cases are present. So, you can see that when b is 1, the output is 1, right, and these two can be grouped together, and by which if in absence of this we would have got a b, y is equal to b. So, these two can be summed together and we can see that there is a I mean these two can be put together and we get a y plus b, y or b representation. So, this is something which we can compare with what we had done in the past and the basic relationship and the truth table, but can we have a generalized rule or method by which we can group these things? We do have such method. Okay. So, for which we look at SOP simplification rule, which is taking forward this discussion. So, for that we look at first a 3 variable representation of the Karnaugh map. So, for the 3 variable representation of the Karnaugh map, we have got 3 variables a, b, c. So, on one side we have got c at 0 and 1, which is similar to what we had seen before, and this side we have got a b. So, 4 possibilities are of a b 0 0, 0 1, 1 1 and 1 0. So, now you remember that after 0 1 we are not going to 1 0, we are going to 1 1, because we are looking for a logical adjacency between two neighborhood positions, two neighboring position, okay, two adjacent positions, okay, which will help us in forming groups, right. So, by logical adjacency what we mean is that between two positions only one value will be changing, one of the ABC value will be changing. So, this particular position you see 0 0 1, this particular position is 0 0 1 a bar, b, c bar, and here next one is this particular position is 0 1 0, next one is 1 1 0. So, only a is changing from a bar to a. So, if it was 1 0, then two values would have changed, a would have changed as well as b would have changed, which we are not allowing here to have a better opportunity or better way of convenient way of formation of the groups. Okay. This we need to take note of when we form the Karnaugh map for 3 variable. Okay. The other side is the same. Now, if we look at one example, so this is the example of a function where the min terms are 2, 4, 5, 6, 7. And we can here again the corresponding min terms, the m0, m1 we are not writing in this manner, we are just writing the decimal equivalent of 8. So, 0, 0, 0 this is 0, this is 0, 0, 1 is 1, then 2, 3, because a b bar 1 0 is coming over here. So, 4 5 is here, right, and then 1 1 0 is 6 and 1 1 1 is 7. So, the min terms are like this is the min term suffix mention of those things. So, here 2 4 5 6 7. So, 0 1 2 2 there is a 1 present over here, right, and 4 5 6 7 4 is here, 5 is here, 6 is here and 7 is here. Okay. So, that way the truth table is converted to 3 variable Karnaugh map. Is it clear? Right. Then how we form the group? We look at largest logically adjacent group of size which is in integer power of 2. So, integer power of 2 is what? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 like this. Okay. So, that means size of 2, 1, 2, 4, 8. So, these are the different things that you are looking for in while forming the largest group. Okay. So, and they should be logically adjacent, right, and in the form of a rectangle like this, which is very clear here. And while talking about logically adjacent, more we shall discuss little later. So, the groups that we can form here, you can see this is the group of 4, largest group of 4 that we can form, and this is another group that we can form over here which covers all the ones, right. So, in the SOP realization all the ones need to be covered. Okay. And each group will give us one product term, the way we had seen in the previous example. So, one was giving A, another was giving B, and we had a summation of A and B to get y is equal to A plus B for the second example for a 2 variable case we have seen before. So, here this particular group when we are looking at, so the product term that will come out of it, we shall see which variable is remaining constant within the group, that means which is not changing, right. So, if you see within this group C is changing from C bar to C along this direction, and along this direction B is changing from B to B bar, B bar to B, right. So, only A is not changing. So, this product term will have only one variable which is A, and other variable since it is changing it is not to be there. So, this will form one product term, and this is another group. In this group again we shall see which is not changing. So, we see that B is not changing, right, and C is not changing and remaining with the value C bar. So, this will generate a product term B C bar, right, and we know that for this particular group A is changing from A to A bar. So, together when we sum it up we get A plus B C prime, that is the SOP realization of this particular truth table. Okay. So, whenever so if we put it in the form of a rule, so largest logically adjacent group of size 2 to the power I, that is integer power of 2, we shall see minimum number of all groups to cover all ones. Okay. Each group will give one product term, variables remaining constant form the product term that we have said, and if it is variable remaining constant with a value 1, okay, it will be unprimed, and if it is 0 it will be primed. Okay. So, variable remaining constant here with say 0 C prime, so we will go there, and B over here remaining with 1. So, only B is going as unprimed or uncomplemented, and all product terms are finally summed. Clear. So, this is the way we shall form the SOP with the Karnaugh map based simplification. Now, we can extend it to 4 variable Karnaugh map. Okay. So, for 4 variable Karnaugh map we shall be having a rectangular space where 16 different possibilities, 16 different locations will be there. Okay. So, you can see one side is A B, another side is C D. So, this side is A B and this side is C D. So, AB is having value 0 0 0 1 1 1 as I said, because we want logical adjacency, after that 1 0, right. Similarly, for CD 0 0 0 1, after that 1 1 because of the need of the logical adjacency, and then there is 1 0. Okay. So, the corresponding min terms, the suffix, the decimal equivalent will be 0 1, since it is 1 1 here. So, 1 0 over here. So, 2 comes after 0 1, there is 2 over here and then 3, 4 5 6 7 here, because of 1 1 present here, 8 9 10 11 and 12 13 14, and here there is a 15. Okay. So, that is the 4 variable Karnaugh map. The min terms they are where are they are positioned. So, if you take this example, so in this example we have got min terms 0 1 2 6 8 10 13 14, just one example. So, 0 over here, 1, this is 0 1 2, right, then 6 6, this is 3 4 5, this is 6, okay. Then this is 7, so this is 8 9, this is 10, okay. Then this is 11, this is 12, right, and this is your 13 and this is your 14. Okay. So, all the min terms are represented in the truth table in the Karnaugh map. So, you can see these their presence. Now, we have to form the largest group of size 1, 2, 4, 8, I mean depending on how you can associate logically these groups. So, what we can see, these 4 ones can be grouped together, right, and what product term it will generate, the variables that are remaining constant. So, C and D are remaining constant, C with a value 0 and C with a value 1 and D with a value 0. So, C D bar will be the corresponding product term, right, and A and B are changing along this group. Okay. Then the other group that is possible we can see over here, this is the other group, this yellow background. So, for that A bar, B bar and C bar. So, this is what is remaining constant, okay, and D is changing from D to D bar over this particular group. For this one, it cannot be grouped with any other. So, this is all the variables come into picture, A, B, C prime, D, A, B, C prime, D. So, A, B from this side and C by C prime, D from the column side. Okay. Now, comes the interesting part, which I was saying, that while these are evident, we need to take note that the one that are in the edges. So, in the edges, say this particular one, this location is A, B bar, C bar, D bar, and you look at the other one, this is A, B bar, C, D bar, and this one is A, B bar, C bar, D bar. So, this is this location, this is this location. Okay. Now, between these two locations, what do you see? That A, B bar, C bar. So, this is A, B bar, C bar, and only the D is changing from D to D bar. Okay. So, only one variable is changing. So, though they are physically not adjacent, but they are logically adjacent. So, if nothing else is there, only this one and this one is present, that means this one and this one is present, we can form a group of these two. Okay. And what will be remaining constant, what term it will be there? A, B prime, C prime, because D is changing. So, that will be the corresponding term. So, that way all these 4 corner terms, the one that is shown with this brown this thing, they can be grouped together, and the term that is remaining constant for them you can see is B prime. B prime is constant for all these corners, right, and also D prime is constant. So, B prime and D prime is the other term. So, this is valid for 3 variable and problem as well. If we look at those corner values, we can see a logical adjacency. So, ultimately the 4 terms that we product terms, we sum it up and we get the corresponding Karnaugh map representation. Okay. So, now we look at the use of do not care in the Karnaugh map. Okay. So, in the what do we mean by do not care? So, some of the input combinations which is of no interest to us. For example, if we have a design problem, where the input to a circuit is binary coded decimal. That means only decimal number coded with binary. So, decimal numbers input is 0 to 9. So, the binary coding is 0000 to 1001. Okay. These are the inputs. So, and for that whenever the input is odd, okay, that means 1, 3, 5, 7, 9, the output will be high, otherwise the output will remain low. Now, for these 4 variable inputs, when you form the Karnaugh map and all, so there are 16 possibilities. So, beyond 0 to 9, that means 10 to 15, the decimal equivalent, you do not have you do not need to care, because those inputs will never come. Input is mentioned as a BCD input, binary coded decimal input. So, we write in SOP this in the min term representation. So, M min terms 1, 3, 5, 7, 9, and these are the do not care, 10 to 15 are the do not care. And in the truth table, though they go as a x, x means it could be either way, 0 or 1, we do not care actually. Okay. So, in the Karnaugh map mapping, how it will reflect? So, in the Karnaugh mapping, so wherever your this min terms 0, 1, 2, this is 3, this is your 5, this is your 7, and this is your 9. Those ones will be present, rest are 0 up to 0 to 9, and 10, this is your 8, 9, this is 10, okay, 11, 12, 13, 14, 15. So, these are all do not cares. Okay. So, now how you form the largest size group. So, to start with, if you do not know how to handle the do not care and all, you are a bit circumspect. So, you may ignore them and you just try to form the largest group possible with the help of to cover all the ones. So, in that case, the largest group possible over here is this is 1 and this is another one that I said the edges they are logically adjacent, and you get from this one A prime D and the other one you get B prime C prime D. So, this is the expression that we will get. But when you do that, effectively what you are doing, you are considering these do not care as 0, is not it. Since you have not covered it, if you just put the value say 1010, that is your decimal 10, the output here generated will be, if you just substitute those values, y will become 0, right. So, effectively you are treating them as 0, while we have the option of treating it as 0 or 1 because we do not care, right. So, if you consider the x as do not care, that you can consider it as 1 if it helps you in forming the larger group size of integer power 2, then you can go ahead with that, and in doing that you can see this 3 do not care condition can be considered as 1 and a larger group size can be formed, and one particular group can cover all the ones, because there is the necessity that all the ones need to be covered, and in this particular group you can see that only D remains constant and rest of the things A, B and C changes. So, Y becomes D. Okay. So, whenever it is convenient we shall use do not care as 1, that means it helps in making a larger group size. And it is also evident if you look at this truth table, this is your D and this is your Y, right. So, we look up to 1001 this particular case, right, and we see whenever D is 0, output is 0, D is 1, output is 1, D is 0, output is 0, D is 1, output is 1. Okay. So, this is also evident from the way if you the truth table is formed. Okay. Now, this can be used for POS, that means product of some representation also. So, for that we look at some example. So, the example that you have seen for the 3 variable case 2, 4, 5, 6, 7. Now, from max term point of view where zeros are to be covered. Okay. So, the max term are 0, 1, 3. So, these are the max terms that are need to be covered. So, these max terms when you cover it, you will find this is 0, 0 that is remaining constant for this particular group. So, 0 for max term based representation we know whenever 0 it will go as uncomplemented, and whenever it is 1 it will go as complemented. So, the sum term that is formed here is A plus B, and in this case A is remaining constant with 0. So, A will become go uncomplemented, and B is remaining constant with 1. So, C is remaining constant with 1. So, C will go complemented. So, C bar. Okay. So, these are the two sum terms which we, if you just AND it, you will get the minimized POS representation. And if you look at from distributive law, if you apply, you will get A plus B C prime, which we got for the SOP based minimization, where we considered all the ones. Okay. So, what we saw for do not care condition, so similar thing can appear for this do not care condition in the POS representation also. So, the same example that we had seen before. So, the zeros that represents the max term. So, 0, 2, 4, 6, 8 even positions, they are zeros. So, that is the, those are the max terms, and 10 to 15 are the do not care values. So, this is what you see over here, these 10 to 15 remain the do not care value. Now, you have to form the largest group of zeros. Okay. So, here again at the edges we have logical adjacency. So, the largest group that can be formed is by considering this and this, and over here what remains constant? You see that only D remains constant with a value 0, and for SOP POS representation, D remaining constant with a value 0 means its uncomplemented version will come into the sum term that is formed, and only one sum term is formed. I mean, there is no other term and no other variable. So, A is equal to D. Okay. So, the rule says to cover all the zeros, variables remaining constant from the sum term, 1 is primed and 0 is unprimed, product of all terms are considered, and x is considered 0 wherever helps in forming larger sized groups. Okay. So, dual circuit is something which is useful that we would like to discuss in this context. So, the kind of circuit that we had seen before, that was two level representation considering all the max terms. Now, in the in that particular consideration we had seen, for any SOP we can convert to NAND and any POS we can convert to NOR irrespective of whether it is a min term based representation or a max term based representation by using De Morgan's theorem, first kind and first theorem and second theorem for two respective cases. This we discussed in the last class. So, here also if we take up look at this particular example. So, this is one particular truth table. Okay. So, this is the corresponding NAND representation, that is fine. So, if you want to get this particular truth table, the representation using NOR. Okay. So, basically we are talking about POS representation, right. So, POS representation we have to consider all the zeros and we can get directly the NOR circuit from this by the discussion that we had before. Another way of looking at it is, first you consider this was y, you consider y prime. Okay. So, y prime is what? Its inversion. So, wherever there was 0, there will be 1. So, these are the cases. So, the corresponding circuit that you get over here by considering these two groups A prime B and A prime B C prime, is not it? This is A prime B C prime. So, this is what you get, and this is your A prime B. Okay. So, from that you get the corresponding NAND circuit instead of AND OR circuit. Now, if you look at this particular circuit, NAND can be converted to from this this De Morgan's theorem, A bar plus B bar. So, that means bubbled OR. So, this is what you are doing, this NAND gate becomes a bubbled OR gate. Okay. So, this is NAND gate also becomes a bubbled OR gate, that means A bar, these are inverter that is put in the before the OR gates. So, this inverter can be brought over here. So, A becomes A prime becomes A and B becomes B prime. Okay. So, now these bubbles over here can be brought to this place. Okay. So, that this becomes an OR gate, and finally, this output y, it was y bar. So, if you take another bubble inverter of it, it becomes y. Okay. So, this becomes your POS representation by simply converting this particular circuit to the other circuit, where NAND gates are converted to NOR, NOR will be converted to NAND and complement all inputs and outputs. So, these were the inputs you see. Okay. These inputs are complemented and complement all the outputs. So, this is also output that is getting complemented. So, this is the way you can get a dual circuit. So, from NAND you can get NOR or NOR you can get NAND, that means NAND is replaced by NOR, NOR is replaced by NAND, and all outputs and inputs are complemented. Okay. So, the last slide of this particular discussion. So, there is something called self dual function. So, what is a dual function? Dual function is something where if you change the AND with OR and OR with AND, okay, what you get is the dual of the given Boolean function. So, if this is the function, then a given function, its dual represented in this manner is in place of AND you are putting a OR, and in place of OR you are putting a AND, okay, and this is AND. So, this is OR. Okay. So, if you simplify, then you get this one. So, obviously, you can see that these two are different. So, these are not self dual, this is the dual and the function is different, which is possible. Okay. But if you look at another function, say AB, BC and CA, AB plus BC plus CA, okay, this is the one, and again you take dual of it, that means change AND to OR and OR to AND, you get A plus B ANDed with B plus C ANDed with C plus A, and if you simplify it, you get back after the simplification steps the same function. Okay. So, this FD and this FAB, they are self dual. Okay. So, if you change the AND and OR, there is no difference, okay, for such functions. So, when we can when a particular function becomes a self dual, so is there any rule? Yes, there is. So, for that let us look at their truth table. So, if you look at the truth table of the one where it was not dual, self dual. So, this is what you get, this is the one. Okay. Sorry, there is some issue today. Anyway, you can find out that the issue, these are the two min terms that are there, and if you expand this particular case, the corresponding min terms are A prime B C, A B prime C, A B C prime and A B C. Okay. In this case, A prime B and A B prime. Okay. Right. Now, one thing that is required for a function to be self dual is that it needs to be neutral. That means, the number of min terms will be same as number of max terms. What does it mean? That number of zeros in the function output will be same as number of ones in the function output. So, if it is a 2 variable case, 2 zeros and 2 ones, 3 variable case, 4 zeros and 4 ones. If it is not satisfied, then it is not, cannot be a self dual function. Okay. So, that is first condition, but that is not sufficient. This is a necessary condition, not sufficient. So, another requirement is the function must not contain mutually exclusive min term. Okay. So, what do you mean by mutually exclusive min term? So, if there is a min term like A B C, okay, its mutually exclusive min term is A prime, B prime and C prime. If there is a min term like A prime, B, C, its mutually exclusive A, B prime and C prime. Okay. So, this is its mutually exclusive min term. So, they should not be part of the mutually exclusive term should not be part of the Boolean expression, then it will not be self dual. So, in this particular case you can see that A prime B C, its mutually exclusive term is A B C prime, this one its mutually exclusive is A B C prime, okay, but A B C prime is not part of, is this min term is not there. So, this A B C prime is where here, sorry, A, its mutually exclusive is A B prime C prime. Okay. So, where is A B C prime? So, this is A B prime C prime. So, this is 0. Okay. So, that way you can see that this particular function is self dual because it satisfies both the cases. Okay. So, anywhere it will be wherever you see some such cases, if you examine you can find self dual function, and for which if you just change the AND and OR, the circuit will may look different, but the function output will remain the same without any alteration in the input output relationship. Okay. So, with this we conclude, and to summarize, logical adjacency is key to Karnaugh map based representation and simplification. In SOP simplification, all ones need to be covered with minimum number of largest integer power of 2 sized logically adjacent groups. In POS, it is coverage need to be done for zeros, and don't care conditions at the input side can be treated as zeros or ones depending on whether it helps in getting a larger sized groups and a minimized expression. And duality at circuit level can convert from AND OR to OR and for self dual function changing and OR we get the same function and does not make any difference, but from the requirement of AND OR gate may become different. Okay. Thank you.